Hi, y'all. This video will deal with the force that a charged particle experiences when it's in a magnetic field. So we'll go ahead and get started on that. So the easiest thing to do to start with is just to look at the size of the force that a charged particle will experience. Um, and the size of that force is proportional to the charge itself, um, the velocity with which the charge is moving, the magnetic field that the charge is moving in, and then the angle between the magnetic field and the velocity of the charge. So a couple things here. We've got this B right there. B is the variable that we're going to use to stand for magnetic field. And magnetic field gets measured in units of Tesla, which is right there. So we're going to do an example problem here real quick, but I also want to stress that the angle theta that we have, that's the angle between the velocity of the charge and the direction of the magnetic field. So say if we had maybe a charged particle that was moving in that direction, and then maybe we had a magnetic field that was directed to the right there. Then that looks like about a 90-degree angle to me. At least that's what I was shooting for. But at any rate, that angle right there would be my angle theta that I would use in this particular formula. One other thing I'll note is the fact that the charge, we're figuring out the magnitude of our force, the size of our force. So we're always going to use absolute values there on the charge. So we'll take a look here, at least we'll try to, at the next slide. And so there's a couple consequences of this formula if we think our way through it. In order to have a force on this charge, on some moving charge, then the charge has to be moving. The size of the force is QVB sine theta. So again, F is equal to QVB sine theta. So we can see there, if the velocity is zero, then there's no force. Obviously, if the magnetic field is zero, there's no force also. If our object is neutral, so if our object has no charge or has a balanced charge, then there's no force. When would the force be maximized? When would the force be the largest? Well, that happens when theta is equal to 90 degrees. So in this case right here, where theta is 90, what's the sine of 90 degrees? If we can remember that, plug it into a calculator. Sine of 90 degrees is equal to 1. Okay, so, and that's as large as sine can be. What about this right here? What would the angle be in that particular instance? Well, the velocity and the magnetic field are pointing in the same direction. In this particular instance, theta would be equal to 0 degrees. What's the sine of 0? It's 0, so there would be no force. All right. So in order to have any kind of force at all, what we have to have is that the velocity of our charge has to have some component that's perpendicular to the direction of the magnetic field. That's another kind of a complicated way of saying that sine can't be 0 or 180 if I actually want to have a force. Right. Let's take a look at an example problem. So in this problem, we've got an electron moving at a speed of 3.5 times 10 to the 6 meters per second. It's moving in a magnetic field that is 50 millitesla. And we are asked to calculate, the force on this charge. So the first thing I'll do maybe is try to draw this out. We've got a charged particle there moving with some velocity v. It's moving in a magnetic field. The magnetic field is to the right here. Those are all supposed to be horizontal lines. Sorry, my bad. And so that angle right there is 30 degrees. All right. Okay, so we can figure this one out pretty readily. We're just kind of plugging and chugging our way through. Let's see, the charge on an electron is what? Negative 1.6 times 10 to the negative 19 coulombs. And now it really is, it's just a case of plugging and chugging our way through. F is equal to QVB sine theta. So this is going to be what? 1.6 times 10 to the negative 19 coulombs. Notice there I've dropped the negative sign because, well, we've got absolute values on the charge. 3.5 times 10 to the 6 meters per second. This says what? 50 millitesla, so that would be 0.05 Tesla. And then times what? The sine of 30 degrees. And I ran out of space. But when I do all that, I end up with a force that is, let's see, 1.4 times 10 to the negative 14 newtons. All right, so that's that answer. And that actually is the only thing I was asked for. But a lot of times when we figure out force, we also maybe want to know acceleration. So I could ask about the acceleration of this electron. Well, if I want that, I can pull out my old friend Newton's second law, F equals ma. To figure out acceleration, I'll plug in 1.4 times 10 to the negative 14 newtons. Mass of an electron is 9.11 times 10 to the negative 31 kilograms. And as a result, I get an acceleration that is about 1.5 times 10 to the 16 meters per second squared. Which, yeah, that's the valid answer here. And that number seems huge, but that is the valid answer. Now, if we were in class, I would ask, you guys satisfied with this? Have we answered everything? Are we good? And hopefully somebody would yell, well, no, because force is a vector and we don't just need the size, we need the direction as well. So that's kind of a question that we're left with here is, well, what is the direction that our force points in? What is the direction of this acceleration? Okay. All right, so big old mess. So hopefully we understood calculating the force, but we do need to figure out how to deal with the direction of that force and what we're going to use in order to figure that out. So I'll be straightforward here. This would be best done in class. It's going to be a little rough to get this across in video, but we're going to use a right-hand rule, and the way this is going to work is that we can look at the direction that the charge is moving in, and we will put our hand along the direction of the velocity vector v. All right, and we're going to hold our hand in such a way that we can then curl our fingers towards the way the magnetic field is pointed in. By the way, this person seems to have a bit of an issue here, bit of a problem. Where'd the thumb go? All right. Anyway, so we hold our hand in the direction of V. Where's the? Hold our hand in the direction of V. Okay, and then curl our hand in the direction of B. And what's going to happen is our thumb is going to point in the direction of the force F. Okay, so that magnetic field B is exerting a force F on this charged particle that's given by, well, at least the direction is given by this right-hand rule. Put your fingers in the direction of the velocity, curl your fingers in the direction of the magnetic field, and your thumb should show the direction of the force. All right, well, that's great for positive charges, but what if we have a negative charge? Well, if we've got a negative charge, then the direction of the force just gets reversed. Now, that makes sense. That happens often when we talk about direction of forces. All right. A couple little reminders on notation for vectors. If we've got a vector that's pointing into the page, then we represent it with this kind of arrow and cross, or with this kind of cross, kind of like the back of an arrow moving away from you. So this is for a vector pointed into the page. If we've got a vector coming out of the page, then it's like the arrowhead's pointed straight at you, which sounds dangerous. All right. And then what we have next is, well, we'll look at maybe the behavior of a charged particle in an electric field versus the behavior of a charged particle in a magnetic field. So up at the top there, we see our charged particle moving in an electric field. And we can remember that, well, that force on a charged particle is equal to Q times E. All right, so the direction of the force there is either in the direction of the electric field or in the exact opposite direction of the electric field, depending on whether the charge is positive or negative. Now, on the other hand, if we look at this charged particle in a magnetic field, what we end up with is that the force is actually perpendicular to the magnetic field. Also, the force is perpendicular to the velocity vector. And that's exactly what we see here. For instance, if we look right there at that moment, and we think about it, we put our fingers in the direction of the velocity vector, we curl our fingers in the direction that the magnetic field is pointed in. So if I try to maybe stop this share here, stop share, okay. If I point my fingers here in the direction of the velocity vector, and then say the magnetic field was pointed that way, I curl my fingers in the direction of the magnetic field, my force would be straight upwards. Okay. All right. So let's see what's next here. We've got a question. So this question says that we've got a positively charged particle. It's moving in some region of space that has a magnetic field, or actually, what's it say? I misread it, I'm sorry. It says it's stationary in a constant magnetic field. Which of the following statements has to be true? Pause the video, think about it. Here's the answer. Well, the one that's true is, well, the particle's not going to move. If the particle is stationary, if it's stationary there, then well, that means its velocity is zero. That means that the force is going to be zero. That means it's just going to sit there forever. As a matter of fact, a magnetic field can't change the speed of a particle. It will cause an acceleration, but that acceleration only causes a change in the direction of motion for this charged particle. It will never cause a change in speed. So if the particle's sitting still to start with, it's going to sit there forever. All right, let's see here. What's next? What's next is a bunch of practice with this right-hand rule. So we'll save that for the next video, though. All right.